So in this video, I'm going to talk about truth tables. And so in order to talk about truth tables, we need two basic ideas. The first basic idea is the notion of an interpretation function. And so an interpretation function, which I'm going to represent with this word I, or this letter I, what it does is it's a function and it takes propositional letters or variables. So we might take P, Q, R, all the way to Z. It's going to take these variables as an input, and as an output, what it's going to do is assign them a truth value, either T or F, not both and not neither. So the notion of an interpretation, you can think about it as taking a propositional letter or variable, and it's going to say, I'm going to interpret the value of P. I'm going to assign it a truth value, and I'm going to state that the value of P here is true. And it's going to keep going through all the letters. It's going to take Q and then evaluate it or assign it a truth value of false. It's going to go through all the letters of the language and assign it a truth value. True or false, not both and not neither. So the first notion you need is the notion of an interpretation function. The next notion that we need is the notion of a valuation function. What does a valuation function do? Well, a valuation function works a little bit different. What it does is takes either, at least in classical logic, it takes a truth value, let's say T or F, and it outputs or gives you another truth value, T or F, not both, not neither. But this is not the only kind of valuation function. Some valuation functions, instead, what they'll do is take a truth value, T or F, from one collection or set, and also take a truth value from another set, and it'll give you one and only one truth value, either T or F. Okay, so what does this second one mean? So I think it's pretty easy to understand. The first one, if you have a value of true, then it's going to output or give you a value either T or F. Well, in the second one, what's happening here is it's taking one of the values from this set, one of the truth values or members from this first collection. And so let's say it takes a value of true, and then it's going to take another value from the second collection. Let's say it takes false, and then it's going to output one and only one value, T or F. So it's going to make more sense in practice, but these are the two basic notions that are fundamental for understanding truth tables. So let's look at a particular example of this. So let's say we had the well-formed formula, I'm going to use it. So let's say we had the well-formed formula not P. Well, when we think about this particular formula, we see how many ways are there of interpreting it. And remember, an interpretation is an assignment from propositional variables or letters, truth values. How many different ways can we interpret P right here? Well, there are really only two. We can assign it a value of true, and we can assign it a value of false. Any other interpretation is going to do one of those two things, so it just repeats that process. The next thing to note is, well, now given that we have a truth value assignment, we have a value assigned to P here. What this negation signifies is a particular valuation, particular way of taking a truth value assigned to a formula or a proposition and outputting another truth value. It says that if you give me a truth value, T or F, I am going to give you another one and only one truth value. So in the case of negation here, it does what you probably already know it does. It says if you give me a value of true, then I'm going to deliver you a value of false. Or if you give me a value of false, then I'm going to deliver you or output a value of true. So in the case of not P, our truth table here is just a graphical representation of this. It's just a representation of this valuation in table format. So if P is assigned a value of true, then not P takes a value of false. And if P has a value of false, then not P has a value of true. We're taking this truth value that is assigned to P, running it through this valuation function. We're delivering it as input, and the valuation function is giving us a value as output. Let's take a more complicated example. Let's take another example. In this case, let's take P and Q. We have P and Q here, and we think about how many different ways can we interpret the letters, propositional letters found here. So we have P and we have Q, and we think about, okay, well, what are the different ways I can interpret P and Q? Well, P could be true and Q could be true. P could be true and Q could be false. P could be false and Q can be true. And then P can be false and Q can be false. So in terms of our interpretations, we have 1, 2, 3, 4. So what the valuation function is for this conjunction sign here, or this symbol for and, sometimes you see it represented differently in different textbooks. Sometimes there's this ampersand here. Sometimes it's represented using the dot. What it says is that if you give me two truth values and they are both true, then the output will be true. And in all other cases, the truth value that will be output is false. So in the first interpretation where we have true and true, the output is true. In the second interpretation where we have P is true and Q is false, the output is false, false, and false. It's only in the case where P and Q are both assigned a value of true is it the case that P and Q is true. Next, let's look at disjunctions. So in a disjunction, what we have is a formula P or Q, or PVQ. And so we want to determine the truth value of P or Q. For that, we are going to need some input. So we need an assignment of truth values to P and Q. So again, we have true, true, false, false. And here I'm just listing off the different ways that P and Q can be interpreted. So again, we have 4 interpretations here. And in the case of the or, what it says is that if you give me any truth value as an input, then the output is what the sign for disjunction, or this or, says is that if either one of the truth values is true, then the output is going to be true. So interpretation 1, we have at least one truth value that is true. So in this case, actually both of them are true. So the output is true. In interpretation 2 here, we see, well, we have at least one truth value, which is an input of true, or has a value of true, and so the output is going to be true. In our third interpretation here, we have false and true, and so our output will be true. And it's only in this final case here, row 4, where neither one of the truth values are true, and so the output is not going to be true. Instead, it will be false. So what the sign or valuation function for V or disjunction states is that provided one of the truth values of P or Q is true, then the entire formula P or Q is true. Next, let's look at the conditional. So we have the formula P right arrow Q. And again, there are 4 ways of interpreting this formula. And so it can be true, 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 false, false, true, and false, false. So with these as input, we need to know how this right arrow behaves. And what it states is, there are many ways of expressing this, but one way of putting it is that this formula is false only in one case. It's false only in the case where the first input is true and the second input is false. So it's only false in this one single case right here, and it is true in all of the others. So in all of the other cases, it will come out as true. So an easy way to remember this right arrow, sometimes it's represented using a horseshoe, is that you only need to look at the value of the antecedent, which is this formula P right here. And if that is true, then you need to check the value of the consequent here. And if that is false, this is the only case where the formula comes out as false. Now, if neither one of these conditions, or if both of these conditions don't apply, then you immediately know that the conditional, this P right arrow Q, is true. Let's look at the last example. The last example is the biconditional. And the biconditional is one of the easiest to understand. Again, we have P, Q, and we have the truth values for P and Q. True, 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 false, false, true, false, false. And this valuation function, the way it behaves is that the formula is true just in the case that the input matches. So this valuation function says that provided P and Q have the same truth value, then the formula P double arrow Q, or P if and only if Q, is true, provided. So in the case of the biconditional, this biconditional is true provided P. So in the case of the biconditional, this biconditional is true provided the truth values of P and Q are identical. So let's take a look. In our first interpretation in row 1, P and Q, their truth values are identical, so this formula is true. In rows 2 and row 3, what we see is that the truth values of these two inputs are not identical, and so the values of rows 2 and 3 are false. Again, you see that these two inputs do not match. That is, in this case, in these two rows, the value for P is different from the value of Q. In our final row, row 4 here, what we see is that the values of P and Q match, and so they're both false here, and so P, if and only if Q, comes out as true. Okay, so now that we have the basics down, now it's time to take a look at some more complex examples. So let's say we had a formula, and let's say it's not P and not Q. And we want to use a truth table to determine the truth value of this more complex formula. So the process again is the same. We look to see how many propositional letters that there are, and then we need to come up with an interpretation that covers all the different ways that these propositional letters can be interpreted. So let's write our two propositional letters over here, and then think about the different ways that these propositional letters can be interpreted. And since there are two propositional letters here, it's 2 to the n, where n equals 2, what we're going to have is 4 possible interpretations. And so we'll again have our usual true, 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 false, false, true, and then false, false. All right, so now that we have our 4 interpretations, 1, 2, 3, 4, we want to complete the truth table. Now, we can do it in a more step-by-step fashion by taking the information and under P right here, the interpretation, and writing true, true, false, false under P. And what we're doing and saying is that if P is interpreted in this way, then the valuation of P is also true. But we're going to skip a step here and go directly to determining the truth value of not P. And one thing what we would note is to say, well, if P takes the value of true, then what does the valuation function for negation say? It says, well, if P is true, then not P is false. And if P again is true, not P is false. What we're doing is going row by row and saying, well, let me take the value of P and run it through this negation valuation function, and then write down the corresponding truth value. And what this is telling us is the truth value for not P right here. We're determining the truth value of this formula in the context of this broader formula. Now, line 3, we have P, and it has a value of false. And so when we run it through the negation function, it gives us a value of true. And the same thing for line 4. Now, when we go to Q, remember what we're doing is taking the truth value of Q and then running it through the valuation function for negation. So if Q, according to row 1 here, is true, so we see that it is true. So we could even write true right here. Then the truth value for not Q is false. And again, if the truth value for Q is true as determined by the interpretation, that is, and again, if we see that the truth value of Q is false right here at line 2, that is, the interpretation of Q is false, then the truth value of not Q is true. And if Q is true, then not Q is false, according to line 3. And on line 4, we have an interpretation of Q as false, and so the valuation of not Q is true. And so what we've done here is determine the truth value of not Q. Now that we have the truth value of not P for every interpretation, and we have the truth value of not Q for every interpretation, what we're going to do is we're going to take these truth values, F and F, F and T and F, T and T, that is the truth values assigned to these two formulas, and we're going to run it through the conjunction valuation function. So let's do that right now. Let's take those truth values and run them through the valuation function. The thing to point out is you are no longer going to look at the truth values over here. We're no longer concerned with the truth values of P and Q. We're concerned with the truth values of not P and not Q. We're going to use those truth values and the conjunction valuation function to determine the truth value of the entire formula. So if you remember, the truth valuation function for conjunction says that provided both of the inputs are true, then the output will be true, and it will be false in all other cases. So we can quickly scan this row by row and take a look. And we see only in this 4th row do we have true and true. In all the other rows, we have at least one F. So in this case, we have a false. In this case, we have a false. And in row 1, we also have a false. So what we've done here is determine the truth value of this formula for every way you could assign truth values to it. So in row 1, if the interpretation of P and Q is true and true, then not P and not Q would be false. But if P and Q were both false, then our formula, not P and not Q, would be true. Let's look at one more example. So in this last example, what we're going to look at is, we're going to look at two formulas. So we'll look at not P and Q, and then we'll look also at not P and Q. So the reason why I want to look at these two particular formulas, and they're similar to the ones that we looked at already, is because there's one small difference between them. And that difference is the fact of the parentheses. So I'm going to quickly write down the various interpretations of P and Q. And I'm going to try to be as neat as possible. And the next thing I'm going to do is we're going to go about determining the truth values of these formulas. So in the case of Q here, we don't really need to do much. We only need to take the interpretation for each row and write down the corresponding truth values. So we have true, false, false. I'm not doing anything special here. I'm just taking the interpretation of truth value that's determined by the interpretation and writing it down under Q. In the case of P, I need to do a little bit of work here. I need to flip the truth values. So for row 1 here, since P is true, well, it's going to give me not P. And then we have true, false, and then row 3 we have false, so it's going to give me true. And row 4 we have false, and so that's going to give me true as well. Now I'm going to take the truth value of not P and Q, put them together, and that's going to ultimately give me the truth value of the entire formula. So I'm going to take the truth value of each of these two formulas. So again, it's a conjunction, and so we need 2 truths in order for the whole formula to be true. And we only get that at line 3 right here. And in all other cases, it is going to come out a value of false. So this is instructive. What it says is that for each one of these interpretations, we can determine the truth value of this formula or sentence. And provided we know the interpretation, we can determine the truth value of the whole complex thing. Now, I want to actually contrast this with the formula over here. And I want to draw attention to these parentheses. Now, there are a couple of things to point out. The thing to point out is that I want to point out is the way you would complete the truth table. In this particular example, what you would do is determine the truth value of P and Q first, and you would determine the truth value of this whole complex formula. And whatever truth value this has, then you would run it through the negation. So to contrast the two formulas, in this first formula, not P and Q, not P has what's called narrow scope. It only applies to P. It doesn't apply, it's not negating the entire formula. And so when we determine the truth values of this formula, we determine the truth value of P first, then we determine the truth value of not P. In this other example here, we're first going to determine the truth value of P, Q, then P and Q, and then we'll use the truth value of this whole complex formula and run it through the negation function. The way you know the difference between these two formulas is because you have these parentheses. These parentheses are telling us that this negation just isn't applying to P like it is in this first example here, but it's applying to this entire formula here. It's going to take the truth value of this entire formula. So let's complete this. So I'm going to determine the truth value of this conjunction P and Q straight away. Since I know a conjunction is only true when it takes 2 true truth values as input, I will quickly look at the interpretation function over here and see that only in row 1 is P and Q both true. And in all other cases, it comes out false. Now that I've determined the truth value of P and Q, I will take the truth values here and run them through this negation function. And what do I find? What I find is when negation takes a value of true, it gives me false. And in all other cases, it will come out as true. And so one thing to point out here is that these two formulas, not only do they look different, but they are actually mean different things. They come out true and false under different scenarios. You'll notice that this not P and Q is true in every case except for one, whereas not P and Q, the first formula that we're looking at here, is false in every case except for one. It's only true in one case. So this is just to point out that parentheses make a big difference in terms of the truth values of various formulas.